The Antikythera mechanism. In 1901, Greek sponge divers exploring a Roman shipwreck off the coast of Antikythera discovered something that would challenge everything we thought we knew about ancient technology. Among the scattered treasures and corroded bronze lay fragments of what appeared to be an elaborate machine. At first, archaeologists dismissed it as navigational equipment or an astrolabe. But as researchers began examining the device more carefully over the following decades, they realized they were looking at something far more sophisticated than anything that should have existed 2,000 years ago. The mechanism consisted of at least 30 bronze gears housed in a wooden frame roughly the size of a shoebox. When X-ray analysis was finally conducted in the 1970s, researchers discovered the true complexity of the device. The gears were cut with extraordinary precision, featuring triangular teeth that reduced friction and improved efficiency, a design principle not seen again until the Renaissance. The mechanism could predict solar eclipses, track the positions of planets, and calculate the timing of the Olympic Games decades in advance. It was, in essence, an ancient analog computer. What makes the Antikythera mechanism truly extraordinary is not just what it did, but the level of mathematical and astronomical knowledge required to build it. The device incorporated the Metonic cycle, a 19-year period used to predict lunar phases, and the Calypic cycle, which refined these predictions over 76 years. It tracked the irregular motion of the moon using epicyclic gearing, a concept that wouldn't be formally described until the work of Islamic astronomers nearly 1,000 years later. The craftsmanship required to manufacture such precisely interlocking gears would not be matched until the development of mechanical clocks in 14th century Europe. Modern attempts to reconstruct the mechanism have revealed just how advanced it was. Engineers using computer-aided design and precision manufacturing tools have struggled to replicate the device's functionality. The original craftsmen worked with hand tools, yet achieved a level of accuracy that seems impossible given the technology available in ancient Greece. Several gears in the mechanism measure less than 1 millimeter in thickness, with teeth so fine they could only have been carved by someone with exceptional skill and possibly magnification tools we have no record of. The mystery deepens when we consider that no similar device appears in the historical record until over a millennium later. Ancient texts mention mechanical devices and automata, but nothing approaching the complexity of the Antikythera mechanism. This suggests either that such technology was far more common than we realize and simply hasn't survived, or that the mechanism represents a singular achievement, knowledge that was somehow lost when the workshop that created it disappeared from history. The Roman shipwreck dates to approximately 65 BCE, but the mechanism itself may be even older. Who built it, and why did this knowledge vanish so completely? Roman concrete. In the heart of Rome stands the Pantheon, a structure completed in 126 CE under the reign of Emperor Hadrian. Its dome, spanning 143 feet in diameter, remains the world's largest unreinforced concrete dome. What makes this even more remarkable is that after nearly 2,000 years of weathering, earthquakes, and countless wars, the Pantheon's concrete has not only survived, but has actually grown stronger over time. Modern engineers examining the structure have made a startling discovery: we cannot replicate the concrete the Romans used to build it. Roman concrete, known as opus caementitium, was fundamentally different from modern concrete. The Romans mixed volcanic ash from Pozzuoli with lime and seawater, then added chunks of volcanic rock. This combination created a chemical reaction that modern scientists are still working to fully understand. When seawater interacted with the volcanic material, it triggered the growth of rare crystalline structures, specifically a mineral called aluminum tobermorite, that actually strengthened the concrete over centuries. Modern concrete, by contrast, begins deteriorating almost immediately after construction, with most structures designed to last only 50 to 100 years. The secret lies in the specific volcanic ash the Romans used. Pozzolana, named after the town of Pozzuoli near Naples, contained precise ratios of silicon dioxide and aluminum oxide that created optimal conditions for the crystallization process. But the Romans didn't just stumble upon this formula. They refined it over centuries, creating different mixtures for different applications. For underwater structures like harbors and aqueducts, they used a mixture that would harden even when submerged. For buildings and roads, they developed variations that could withstand different types of stress and weathering. What we've lost is not just the exact recipe, but the empirical knowledge of how to work with these materials. Roman engineers understood intuitively which volcanic deposits produced the best results, how to mix and apply the concrete for maximum strength, and how different environmental conditions affected the curing process. This knowledge wasn't written down in technical manuals. It was passed down through generations of builders, embedded in guild traditions and apprenticeship systems. When the Western Roman Empire collapsed in 476 CE, these knowledge networks disintegrated. The recipes were lost, and with them the ability to create structures that could last millennia. Modern researchers have analyzed Roman concrete extensively, identifying the chemical compositions and crystal structures involved. Yet attempts to recreate it at scale have largely failed. The problem isn't just the materials, it's the entire process. We've forgotten how to select the right volcanic ash, how to mix it in the correct proportions, and how to apply it under varying conditions. Even when we try to follow the ancient formulas, something essential is missing. The Pantheon stands as a monument not just to Roman engineering, but to knowledge we once possessed and then lost, leaving us unable to build structures as enduring as those created 2,000 years ago with supposedly primitive technology. Damascus steel, between 1100 and 1700 CE, bladesmiths in the Middle East forged weapons that seemed almost magical in their properties. Damascus steel swords could slice through European blades as if cutting butter, yet were flexible enough to bend without breaking. The distinctive watery pattern on the blade's surface wasn't just decorative, it was evidence of a complex internal structure that gave the steel properties we still cannot fully replicate today, despite our advanced metallurgical knowledge. The steel originated from ingots of woots, a high-carbon steel produced in India and Sri Lanka. But the transformation of woots into Damascus steel required a forging process so specific and carefully controlled that even contemporary smiths in other regions couldn't reproduce it. The bladesmiths of Damascus, along with those in other centers of Islamic metalworking, possessed knowledge passed down through generations, knowledge that would eventually vanish completely by the mid-18th century. The last true Damascus steel blades were forged around 1750, and despite nearly 3 centuries of research, we still haven't recovered the complete process. Modern analysis reveals why Damascus steel was so extraordinary. The blades contain carbon nanotubes and carbide nanowires, structures that wouldn't be formally identified by science until the late 20th century. These nanostructures formed naturally during the forging process, creating bands of hard and soft steel that gave the blades their unique combination of hardness and flexibility. The watery pattern on the surface was actually a visual representation of this internal architecture. But creating these structures wasn't a matter of chemistry alone, it required precise control of forging temperature, the number of heating and cooling cycles, and the specific techniques used to work the metal. The mystery deepens when we examine what was lost and why. Recent research suggests the disappearance of Damascus steel may have been linked to changes in the source of raw materials. The Wootz steel from India contained trace amounts of certain elements, particularly vanadium and tungsten, that were crucial to the formation of the distinctive nanostructures. As mines were depleted and new sources of iron came into use, the chemical composition of the Wootz changed subtly. The bladesmiths, not understanding the role of these trace elements, couldn't adjust their techniques to compensate. The knowledge was empirical rather than theoretical. They knew what worked without understanding why it worked. Modern attempts to recreate Damascus steel have produced impressive results, but something essential remains elusive. Metallurgists can create steels with similar patterns and even comparable mechanical properties using modern techniques. But the original process, the specific sequence of heating, folding, and hammering that ancient smiths used, cannot be fully recovered. We have the materials, we have the tools, and we understand the chemistry better than the original smiths ever could. Yet we cannot replicate their achievement because we've lost the accumulated wisdom of generations of craftsmen who perfected their art through centuries of trial and refinement. Greek fire. In 673 CE, during the First Arab Siege of Constantinople, Byzantine defenders unleashed a weapon so terrifying that enemy sailors would rather jump into the sea than face it. Greek fire, as it came to be known, was a liquid incendiary that burned on water, couldn't be extinguished by conventional means, and could be projected from bronze tubes mounted on Byzantine warships. The secret of its composition was so closely guarded that it remained a state secret for over 700 years, and when that secret was finally lost, no one ever rediscovered it. The weapon was reportedly invented by Callinicos, an architect and refugee from Syria, though some historians believe he may have refined an existing formula rather than creating something entirely new. What made Greek fire unique wasn't just that it burned intensely. Many ancient cultures had access to petroleum-based incendiaries. What made it impossible to counter was that it ignited spontaneously on contact with water and actually burned more intensely when wet. Contemporary accounts describe it as liquid fire that could pursue enemies across the waves, clinging to ships and men alike. Attempting to douse it with water only made it burn brighter. The Byzantine Empire treated the formula as one of its most valuable military secrets. Knowledge of Greek fire was restricted to a handful of individuals, passed down within certain families under conditions of absolute secrecy. Even the emperor might not know the complete formula. Different specialists handled different stages of production, ensuring no single person possessed all the knowledge needed to recreate it elsewhere. This compartmentalization protected the secret but also made it vulnerable. If the chain of transmission broke, the knowledge would be lost forever. Modern chemists have proposed numerous theories about the composition of Greek fire. Most suggest a combination of petroleum or naphtha, quicklime, sulfur, and possibly saltpeter. The quicklime would react violently with water, generating intense heat and igniting the other components. But this explanation doesn't account for all the properties described in historical sources, particularly the ability to project it from pressurized tubes and its reported effectiveness in various weather conditions. Some researchers have suggested the inclusion of phosphorus or other reactive compounds, but without a surviving sample to analyze, we're left guessing at the exact formulation. The formula was lost sometime during the Fourth Crusade in 1204, when Constantinople was sacked by European crusaders. The workshops where Greek fire was produced were destroyed, and the families who held the secret were killed, displaced, or chose to let the knowledge die rather than risk it falling into the wrong hands. In the following centuries, numerous attempts were made to recreate the weapon. Some produced crude imitations, but none captured the distinctive properties that made Greek fire so feared. Today, with all our chemical knowledge and industrial capabilities, we can produce powerful incendiaries, but we cannot recreate the exact weapon that protected Byzantium for 7 centuries. The knowledge is gone, leaving only historical accounts and unanswered questions. Inca stonework. In the Andean highlands of Peru, massive stone blocks fit together so precisely that a knife blade cannot slip between them. No mortar holds them in place, yet they've withstood centuries of earthquakes that have destroyed countless modern buildings. The Inca, working without iron tools, without wheels, and without written language to record their techniques, created stonework that modern engineers with laser-guided cutting tools struggle to replicate. These structures represent a lost mastery of stone manipulation that we can observe but cannot fully explain or reproduce. At Sacsayhuaman, overlooking the city of Cusco, stones weighing over 200 tons are fitted together in complex interlocking patterns. Some blocks have more than a dozen angles, each cut to fit perfectly against neighboring stones of completely different shapes. The surfaces are so smooth and the joints so tight that the structures have flexed during earthquakes rather than collapsing, the individual stones moving slightly but never separating. Spanish conquistadors who saw these walls believed they must have been built by demons, unable to conceive how humans with primitive tools could achieve such precision. The mystery begins with how the Inca quarried and transported these enormous blocks. The stones at Sacsayhuaman came from quarries over 20 miles away, across terrain that includes steep valleys and mountain passes. Moving a 200-ton block over such distance would be challenging even with modern equipment. The Inca had no wheeled vehicles, no draft animals large enough to pull such weights, and no cranes. Spanish chronicles mention the use of log rollers and massive teams of workers, but engineering calculations suggest this shouldn't have been sufficient for the largest blocks. Some researchers have proposed that the Inca used as yet undiscovered techniques involving levers, counterweights, and possibly controlled landslides to move these megalithic stones. Even more puzzling is how they achieved such precision in cutting and fitting the stones. The Inca worked primarily with stone and bronze tools, bronze being too soft to efficiently cut the hard andesite and diorite used in their finest structures. One theory suggests they used a technique called pecking, where repeated blows with harder stone tools gradually shaped the block, but this doesn't explain the extraordinary precision achieved. Another hypothesis proposes the use of wooden templates and repeated fitting attempts, gradually grinding down high spots until the stones nested perfectly. Yet this would require moving each massive block into place dozens or perhaps hundreds of times, a process that seems impossibly labor-intensive even by ancient standards. Recent investigations have revealed additional mysteries. Some stones show evidence of exposure to extremely high temperatures, leading to speculation about the use of thermal expansion, or even something resembling a primitive thermite reaction to split and shape rock. Other blocks contain small circular indentations that some researchers believe are marks from long-lost metal clamps or tools. The most radical theories propose lost techniques involving plant-based solutions that could soften stone, though no evidence supports this idea beyond certain puzzling features in the stonework itself. What remains undeniable is that the Inca possessed knowledge of stoneworking that died with them when Spanish conquest and disease devastated their civilization in the 16th century. Today, despite all our technology, we cannot recreate their achievements. Baghdad Berry, H.D. In 1936, German archaeologist Wilhelm König discovered an unusual clay jar in the collections of the National Museum of Iraq. Dating to approximately 200 BCE, during the Parthian Empire, the jar contained a copper cylinder and an iron rod, components that seemed strangely familiar to König, who had background in electrical engineering. When he analyzed the artifact more carefully, he reached a startling conclusion. He was looking at an ancient battery, a device for generating electric current over 2,000 years before Alessandro Volta invented the modern battery in 1800. The jar, standing about 13 centimeters tall, had been discovered at Kujut Rabu, a site near Baghdad. Inside the terracotta vessel was a copper cylinder, capped at the bottom and sealed with asphalt. The iron rod ran through the center of the copper cylinder, held in place by an asphalt stopper but carefully insulated to prevent direct contact with the copper. When Koenig filled a replica with an acidic liquid vinegar or wine, both available to ancient Parthians, he generated a small electric current. The design was remarkably similar to modern galvanic cells, with the iron serving as the negative electrode, the copper as the positive electrode, and the acidic solution as the electrolyte. The discovery raised immediate questions. What were these batteries used for? Ancient texts make no clear reference to electricity or electrical devices. Some researchers proposed they were used for electroplating gold onto silver objects, a technique that would explain the remarkably even and thin gold layers found on some Parthian artifacts. Replication experiments showed that a series of Baghdad batteries could indeed produce enough current for electroplating. Others suggested medical applications, possibly for pain relief through mild electrical stimulation, a technique mentioned in some ancient texts though not explicitly connected to devices like these jars. Skeptics argue that the jar may not have been a battery at all. The iron rod might simply have been a rolled-up scroll holder, with the copper and asphalt serving as waterproofing. The electrical properties could be coincidental. However, similar artifacts have been discovered at other sites, suggesting a deliberate design rather than coincidence. What makes the Baghdad battery particularly frustrating is that the original artifact was lost during the looting of the National Museum of Iraq in 2003. Without the ability to conduct detailed analysis using modern techniques, we're left with replicas and historical photographs. If the Baghdad battery was indeed used to generate electricity, it represents a technological capability completely absent from the historical record. Electricity as a phenomenon wouldn't be systematically studied until the 18th century. Yet here is evidence that ancient peoples may have harnessed it for practical purposes. What other applications might they have developed? Did this knowledge spread to other cultures, or was it isolated to this region and time period? Most troublingly, what happened to this technology? If ancient craftsmen could create batteries and possibly even understood electroplating, why did this knowledge vanish without leaving more substantial traces? The Baghdad battery remains one of the most enigmatic artifacts of the ancient world, suggesting capabilities that shouldn't exist in the archaeological record. Mayan astronomical calculations. In the jungles of Mesoamerica, the Maya developed one of the most sophisticated astronomical systems ever created without telescopes. Their calculations of planetary cycles, eclipse predictions, and the length of the solar year were more accurate than those used in Europe until the 20th century. Yet when Spanish conquistadors arrived in the 16th century, they systematically destroyed Mayan codices and suppressed indigenous knowledge systems, leaving us with only fragments of a scientific tradition we cannot fully reconstruct. The Dresden Codex, one of only 4 surviving Mayan books, contains astronomical tables of extraordinary precision. The Maya calculated the length of the solar year as 365.2420 days, compared to the modern measurement of 365.2422 days, a difference of less than 18 seconds. They tracked Venus with such accuracy that their observations covered over 500 years of the planet's cycles, noting not just its position but also how it varied over time. Their eclipse tables could predict lunar eclipses across centuries, accounting for the slight variations in the moon's orbit that European astronomers wouldn't understand until much later. What makes these achievements even more remarkable is that the Maya developed complex mathematics to support their astronomy, including the independent invention of zero as both a placeholder and a number, a concept that wouldn't reach Europe from India until the Middle Ages. They used a vigesimal counting system based on 20 rather than 10, which actually offered certain computational advantages for astronomical calculations. Their mathematical notation, while different from ours, allowed them to work with extremely large numbers and perform calculations involving time periods spanning millions of years. The Maya accomplished all this through naked eye observation, using architectural alignments and careful record-keeping to track celestial movements across generations. Sites like Chichen Itza and Uxmal contain buildings precisely aligned to astronomical events. At Chichen Itza, the pyramid known as El Castillo creates a shadow effect during equinoxes that resembles a serpent descending the staircase, demonstrating both astronomical knowledge and sophisticated architectural planning. The Maya developed cross-shaped observatories called caracals, where priests would observe the sky through carefully positioned windows that framed specific celestial events. What was lost represents not just astronomical data but entire systems of knowledge. The Maya integrated their astronomical observations with mathematics, calendrical systems, religious beliefs, and practical applications like agriculture and civil planning. When Spanish colonizers destroyed the codices, with Bishop Diego de Landa alone burning dozens of books in 1562, they eliminated the written record of centuries of accumulated wisdom. Some knowledge survived through oral tradition and later reconstructions, but much of the sophisticated mathematical and astronomical understanding simply vanished. Today, we can admire the surviving calculations, but we cannot fully recreate the observational techniques, mathematical methods, and conceptual frameworks that made them possible. Persian ice houses. In the scorching deserts of ancient Persia, engineers constructed massive dome-shaped buildings called yakshals that could store ice throughout the summer months, even when outside temperatures exceeded 100 degrees Fahrenheit. These structures, some dating back over 2,000 years, relied on principles of evaporative cooling, thermal mass, and convective airflow that modern architects are only now beginning to fully appreciate and struggle to replicate without mechanical refrigeration. A typical yakshal consisted of a large underground chamber, often dug as deep as 40 feet, topped with a distinctive dome rising sometimes over 60 feet high. The thick walls were made of a special mortar called sarouj, composed of sand, clay, egg whites, lime, goat hair, and ash in precise ratios. This mixture created an incredibly effective thermal barrier, with some walls measuring up to 6 feet thick. The domes were oriented to minimize sun exposure, and many incorporated wind catchers, badgers that channeled cool breezes into the chamber, while venting warm air through strategically placed openings at the top. The system began with ice harvesting in winter. Persian engineers constructed shallow pools nearby, sometimes covering enormous areas, where water would freeze during cold desert nights. At dawn, before the sun could begin melting it, workers would break up the ice and transport it to the yakshal. The underground chamber's design then took over. The thick walls and earth insulation prevented heat from penetrating, while the dome's shape created natural convection currents that drew warm air upward and out through vents. Some yakshals incorporated evaporative cooling systems, with water channels in the walls that absorbed heat as the water evaporated. The constant movement of air through the structure prevented warm pockets from forming and kept the interior temperature remarkably stable. Modern engineers examining these structures have found it extremely difficult to achieve similar results using the same materials and techniques. The sarouj mortar recipe, while recorded in historical documents, depended on precise ratios and mixing techniques that were passed down through practice rather than written instructions. Contemporary attempts to recreate it often result in mortar that either doesn't achieve the same insulating properties or develops cracks over time. The positioning and sizing of the vents, crucial for creating the right airflow patterns, required empirical knowledge gained from building and operating many such structures, knowledge that was never formally codified. What makes yakshals particularly remarkable is that they weren't just functional, they were part of a larger system of passive cooling and water management that ancient Persian engineers had perfected. Ice from yakshals was used not just for food preservation, but for making ice-based desserts, cooling homes, and even medical purposes. The same engineers who built yakshals also constructed qanats, underground aqueducts, and wind towers, creating integrated systems that allowed comfortable living in one of the world's harshest climates. When traditional architectural knowledge was displaced by modern construction methods in the 20th century, much of this empirical understanding was lost. Today, as architects search for sustainable cooling solutions to address climate change, they're attempting to rediscover principles that Persian engineers mastered 2 millennia ago. Roman surgical instruments. In Pompeii and Herculaneum, archaeologists discovered medical kits containing surgical instruments so sophisticated that their modern equivalents weren't developed until the 19th century. Roman surgeons possessed tools and techniques for operations, including cataract surgery, cesarean sections, and brain procedures that seemed impossibly advanced for their time. Yet when the Roman Empire fell, much of this medical knowledge vanished, plunging Europe into centuries of medical regression, where practices that had been routine became lost arts. The archaeological evidence is remarkable. Roman surgical kits included over 200 different types of instruments: scalpels with interchangeable blades, specialized forceps, bone drills, arterial clamps, catheters, and wound retractors virtually identical in design to modern surgical tools. The craftsmanship was extraordinary. Many instruments were made of bronze or iron with remarkable precision. Some scalpels had blades thin enough for delicate eye surgery. Forceps came in various sizes and shapes for different procedures, including specialized obstetric forceps that wouldn't be reinvented in Europe until the 16th century. Roman medical texts, particularly those by Galen and Celsus, describe surgical procedures with remarkable sophistication. They understood the importance of hygiene, though they lacked germ theory. They used wine and vinegar as antiseptics, boiled their instruments, and understood that cleanliness reduced post-surgical infections. Roman surgeons performed amputations with relatively high survival rates, removed bladder stones, repaired hernias, and conducted eye surgeries, including cataract removal through a technique called couching. Military surgeons traveled with legions, treating battlefield injuries and developing techniques that wouldn't be surpassed until modern military medicine. What's particularly striking is how completely this knowledge was lost. By the early Middle Ages, European medicine had regressed dramatically. Procedures that Roman surgeons performed routinely became forgotten. The specialized instruments disappeared, their purposes no longer understood. Medical practice became dominated by religious institutions that often prohibited surgical intervention. Barbers, not trained physicians, performed most surgeries, using crude tools and lacking the anatomical knowledge Roman doctors had possessed. It would take over 1,000 years for European medicine to recover the level of surgical sophistication achieved in ancient Rome. The loss occurred not suddenly, but gradually as the Western Roman Empire declined. The medical profession, like other skilled trades, depended on training institutions, libraries, and professional networks to transmit knowledge. As cities contracted, trade routes collapsed, and literacy declined, these knowledge transmission systems broke down. Greek and Latin medical texts survived in some locations, but without the practical apprenticeship system that had trained new generations of surgeons, the written knowledge became increasingly theoretical and disconnected from practice. Much Roman medical knowledge was preserved in the Islamic world and eventually returned to Europe through Arabic translations, but centuries of practical experience had been lost. Egyptian precision engineering. The Great Pyramid of Giza, built around 2500 BCE for Pharaoh Khufu, stands as a monument to engineering precision that modern builders find difficult to replicate. This structure, originally rising 481 feet high and consisting of approximately 2.3 million limestone blocks, was the tallest human-made structure on Earth for over 3,800 years. But its true mystery lies not in its size but in its precision. A precision achieved without modern surveying equipment, laser levels, or powered machinery. The pyramid's base covers 13 acres and forms a nearly perfect square, with sides measuring approximately 755 feet in length. The accuracy is staggering. The maximum difference in length between any two sides is less than 2 inches, an error margin of just 0.05%. The base is level to within less than 1 inch across its entire area. The sides are aligned to the cardinal directions, north, south, east, and west, with an accuracy of better than 1/15 of a degree. Modern construction projects using GPS and laser technology struggle to achieve such precision over comparable distances. More puzzling is how the ancient Egyptians achieved this accuracy. They had no compasses to determine true north. Their surveying tools consisted of Merkit sighting instruments, plumb bobs, and measuring rods. Yet they aligned the pyramid more accurately than many modern buildings. Recent research suggests they may have used astronomical observations, tracking star positions to establish true north. But this would require sophisticated observational techniques and mathematical ability to compensate for the Earth's rotation. The precision implies understanding about Earth's geometry that isn't reflected in surviving Egyptian texts. The construction techniques present another mystery. Each limestone block weighs an average of 2.5 tons, with some granite blocks weighing as much as 80 tons. These blocks are fitted together so precisely that mortar wasn't necessary, and often wasn't used. You cannot slide a razor blade between many stones. The surfaces are flat to within thousandths of an inch. How did Bronze Age workers achieve such precision with copper tools too soft to efficiently cut limestone and no iron tools? Experiments with ancient techniques have produced rough approximations, but nothing matching the actual pyramid's precision. Inside the pyramid, the Grand Gallery presents another puzzle. This ascending passage rises 28 feet high and extends over 150 feet in length, with corbelled walls. The limestone blocks are cut and placed with such precision that the structure has remained stable for over 4,000 years, bearing millions of tons of stone above. The king's chamber features massive granite beams forming the ceiling, each weighing 40 to 70 tons, placed so precisely that the chamber's geometry could be used as a measurement standard. The precision extends to details most visitors never notice. The descending passage is aligned to Thuban, the pole star when the pyramid was built. Passage angles are precise to within minutes of arc. Air shafts extending from chambers are aligned to specific stars that held religious significance. The pyramid's dimensions encode mathematical relationships. The ratio of height to perimeter base equals pi divided by 2. The structure demonstrates knowledge of the Pythagorean theorem, formally described in Greece over 2,000 years later. What makes this precision even more remarkable is construction speed. Estimates suggest the Great Pyramid was completed in approximately 20 years, meaning workers would have had to place a 2.5-ton block every 2 to 3 minutes around the clock, with sub-millimeter precision. Modern engineers examining the structure have stated frankly that they could not replicate it with the same tools, even given unlimited time. How did ancient Egyptian engineers develop these capabilities? The Great Pyramid was the culmination of centuries of pyramid building, each generation learning from the previous one. Earlier pyramids show the progression of techniques, including spectacular failures like the bent pyramid, where architects changed the angle mid-construction to prevent collapse. Yet after the Pyramid Age ended around 2300 BCE, much of this engineering knowledge was lost. Later Egyptian structures, while impressive, never matched the Great Pyramid's precision. What was lost wasn't just construction techniques but entire systems of knowledge. Astronomical observation methods for alignment, mathematical principles for calculating dimensions and loads, organizational systems for managing thousands of workers, quality control processes ensuring precision, and training programs producing skilled craftsmen. When pyramid building ended, these systems dissolved. The knowledge existed primarily in practice, embedded in guild traditions and master-apprentice relationships. Some was recorded in hieroglyphics, but much practical expertise, the critical details making the difference between success and failure, was never written down. The Egyptian precision engineering that created the Great Pyramid represents a peak of human achievement we can study and admire but cannot fully replicate because the accumulated wisdom of centuries vanished when the network sustaining it disappeared. Conclusion: these examples reveal a disturbing pattern in human technological history. Knowledge isn't cumulative, it can be lost, sometimes irretrievably. The technologies described weren't primitive attempts at modern achievements, they were solutions perfectly adapted to their contexts, representing mastery we struggle to match. The Antikythera mechanism computed astronomical positions with analog precision. Roman concrete grows stronger over centuries while ours crumbles in decades. Damascus steel contained nanostructures we didn't identify until recently. Greek fire burned with properties we cannot reproduce. The Inca fitted stones without tools we consider essential. Ancient batteries generated current for purposes we can only guess. The Maya calculated astronomical cycles with remarkable accuracy. Persian engineers cooled buildings without electricity. Roman surgeons performed operations with sophisticated instruments. Egyptian engineers achieved precision that challenges modern capabilities. What connects these losses is the fragility of specialized knowledge. When Byzantium fell, Greek fire's secret died with guardian families. When the Inca Empire collapsed, stoneworking techniques vanished with master craftsmen. When conquistadors burned Mayan codices, they destroyed mathematical and astronomical understanding. When Rome fractured, surgical training institutions disappeared. When Persian traditions were displaced, passive cooling knowledge evaporated. When trade routes shifted and mines exhausted, Damascus steel production ended. When volcanic ash sources changed and chemistry wasn't understood, Roman concrete couldn't be reproduced. The Antikythera mechanism may represent unique workshop knowledge that died with its craftsmen. When pyramid building ended, Egyptian precision engineering dissolved. The lesson is sobering. We assume technology only progresses forward, that knowledge once gained is never lost. History shows otherwise. Human knowledge exists in networks, institutions, guilds, apprenticeships, communities of practice. When networks break, knowledge breaks with them. Written records help, but many skills cannot be captured in text. How do you write down the feel of metal at forging temperature? How do you describe intuition that tells a master craftsman when a mixture is correct? This tacit knowledge, gained through years of practice and passed through demonstration, can vanish in one generation. What we've lost might be rediscovered. Archaeologists and scientists continue unlocking ancient secrets, but rediscovery requires recognizing what was lost, and understanding that previous generations weren't primitive but solved problems in ways we haven't fully grasped. The ancients weren't inferior, they were different, working within different constraints and sometimes achieving results we cannot match. Their technologies weren't simply less advanced versions of ours, they were sophisticated solutions developed through centuries of empirical refinement. When we dismiss ancient achievements as mysterious or impossible, we reveal more about our own assumptions than their capabilities. The real mystery isn't how they accomplished these things, but why we forgot they ever could.